Online, then they're recording. I'm talking about on campus. All right. You guys missed everything. I'm sorry. Where am I at? What were you asking? I'm sorry. Was I in the middle of answering something? Are you good?
Oh, no.
Yes.
Can you show how you got the 4 - 2?
The which one?
The 4 - 2.
Oh. Plug a 4 in. What's the square root of 4?
Oh.
And then times 2, and then plug a 1 in, right? So pretty cool with these symbols here. So the inner area is related to the antiderivative, but they have to be evaluated between the limits. Maybe. So when I plug a 4 in, I get the area up to 4. When I plug a 1 in, I get the area up to 1. If I subtract those, I get the area between 1 and 4. Does that make sense? No. Shit. All right. Yes.
So you just plugged in e to the 4th power and e for x.
Oh, up here.
Yeah.
When x is e, u is 1. So replace that with 1. When x is e to the 4th, u is 4. So replace that with 4.
Okay.
It's the same idea. Everything that had to do with x needs to now involve u. Everything. And the limits used to talk about what x did. I don't care about what x does anymore. I care about what u does. Which anywhere else is not quite grammatically correct thing to say. Okay. So what about, oh yeah, this one's a lot of fun. This one's a lot of fun here. What do you guys think about that one? This one here. This one's going to be a little bit freakadelic. If you let u equal cosine squared x plus 1, right? That seems to be a good place to start, yes? What's du? 2? Well, 2 cosine x sine x. Say again?
Can you do sin x, cosine x? Doesn't matter.
Doesn't matter. I just wanted to do it sort of like in the order of the derivative. Yeah.
I'll remember that because I got it wrong in the text.
Now, what's the problem with that?
You don't have it. Yeah.
Is it a constant that I'm missing?
No.
It's a function I'm missing, correct?
Yeah.
Okay. So it seems like on the surface, I can't do this. All right. I don't know why I put such an evil problem here, but it did. So what I need to do then, do you see how I'm missing a cosine x right here? I like it. So I can't do this directly. I could either try to attack this with trig identities. Yes? Or I can try to, what's the other thing I could do? Try to see if there's a quicker way to do. No, not that I can see. All right, I don't see a quicker way to do this. What was the point? I'm trying to remember what my point was with this problem. All right, let's put this problem aside for now. I don't want to sit here and take up all my time trying to figure this out. Okay, there was some point to this problem. I can't remember what it was. I think it might be one. Yeah, okay. I think I know what I wanted to do with that, but it's a little gross. Okay, because what we really need to do is we need to get into chapter 6. This one is a little bit more involved than I necessarily wanted to do at the moment. Okay. So the big thing with that really needs to be when you have limits on your integration, when you have a definite integral, the limits are something you need to account for. There's something you need to substitute for. Because they talk about what the original variable's doing not with what the substitution variable is doing. Okay. Oh, Jeff. Paper is my nemesis. Oh, here. Paper. Sort of paper. Paper. Now, we're sort of, okay. Chapter 6 involves a couple of levels of problem. Let me see if you guys are cool with this. Let's talk about this in general. So this, of course, represents the area between f and the x-axis. What if I had another function this would represent the area between g and the x-axis? How do I then get just this area? It's basically something we were just talking about. Yeah. So I would subtract these two integrals. And what's important about the order in which I do this? If the question asks, find the area between the given functions. Yeah, the one that's on top needs to be first. Yes? So what would I have to do if the two functions crossed each other somewhere in the middle? Now, let me go step by step. Does everybody understand what we just did? That should hopefully be very straightforward. The total area minus this area equals the area between. That's very straightforward. So what you can do then, if they ask you, find the area between this function and that function, you can just integrate the difference. Is that cool? This is one of our integral properties. You guys okay? Okay, I like it. Okay. If there was a place where between A and B, where the f function and the g function crossed, and of course we'll call that C, remarkably enough. How would I find the area between the functions? What would this area be? What's on top in that area? Yeah, so this would be integral a to c, f of x minus g of x dx, plus, what would this area be? Integral from c to b, g of x minus f of x. Do you guys get that idea? So there will be problems in the homework where you have functions they give you and they cross somewhere. You got to figure out where they cross. So how would you figure out what C is? How would you figure out what C is? Yeah. Solve this equation. Yeah, find out where they intersect. I like it. Okay. So this section should not be overly insane. It does introduce one thing that is actually in one of the homework problems in 5.5. So let's talk about this for a second. Yep. So we sort of have arbitrarily in mathematics decided everything is a function of x and y is the output. We need to understand now that that's not the way it has to be. So for example, couldn't I have something that looks like this? Is that a function of x?
No.
How do you know? Fails vertical line test. I love it. Is that a function of y?
Yes.
Totally. So this... Somebody knows where we're going. So this could, for example, I could make a very simple problem. I could make something that would work with this. If this was 5 and this was 1. X would be y minus 1, y minus 5. Let me stop for a minute. Does that make sense? Because what would the y-intercepts be? 1 and 5. Now the one mistake I have is this, and that makes it turn that way. Sort of like this is positive x squared, this should be negative x squared. So if I have positive y squared would be like this. So this is negative y squared. Okay, maybe. So how would I find the area in there? Couldn't I, we're not going to do this. Let me just say this very first thing. We're not going to do this. Couldn't I redo Riemann sums? What did I just say? We're not going to do this. So don't forget. Couldn't I just redo all of Riemann sums, and instead of delta x, it would be delta y? And instead of f of x is the height, it would be f of y. Holy shit. Right? Why would I do all that when really I just need to think about it like that? And then it's all the same shit we did before, yes? So all I have to do, if I want to figure out the area from, well, between the y-axis and this parabola, what would I integrate? Now it's going to be dy, yes? Because the thing I'm putting on the inside is a function of y. Let's go ahead and figure this out. What is it? Y squared plus 6y minus 5. Okay. Is that cool? That's what that is? Shabo. And want to integrate from what to what?
1 to 5.
1 to 5. I love it. Now, just to point this out, and that's easy. Yeah, I'm not even going to do it, right? That's easy. Who cares that there's a y there? It could be an s there. We've seen freaking alphas there. Who cares what the letter is? But I want to point this out. You could do everything in terms of x, but then you would have to figure out the vertex. You'd have to solve this for x. I'm sorry, solve it for y, so then you'd have a function of x. I really want you guys to... we are not going to do this. But if you were really against rotating your head, you could. Why would the vertex... Is there one function that defines this in terms of x? Why is there not one thing you just told me? Because there's no function for it. It doesn't pass the vertical line test. So when you solve for y, wouldn't there be a plus or minus? Yes? So that would be the positive and that would be the negative. So you could integrate from 0 to this function minus this function. That would be the area between them in terms of x. Wouldn't that be much more difficult? Yes? Yeah.
Wouldn't it have the same area if you just switched the variables x and y?
Of course it would. And that's what I meant by doing this.
Okay.
Right? I like it. Okay, maybe. And what's really unfortunate is you guys don't get as much practice thinking of functions of y as you do with functions of x. Even though, like you just said, they're effectively the same, but it does require you to think of everything kind of, obviously the other way around. Okay. Now, so that's going to come up, obviously. So let's try a problem out. Let me see. Do I want to do... Maybe I do. Well, let's see. So what if I had... Yeah, let me do this. Let me give you guys this handout. This will be easier. So on one side, I kind of step you through all the steps for the problem. so let's work on this together a bit here. Oh. So do part A. Go ahead and figure out part A. Oh yeah. Oh yeah, that's right. All right, I'm gonna start to catch up to you guys. So they meet at 0, 1, 1, 2, and negative 1, 0. So those are the points where those two functions intersect. Okay. Now, if you go to graph these, 0, 1 is a common point to both. 1, 2, common point to both. Negative 1, 0. That's kind of, I can see there's the straight line. That's nice. Yeah, let's do you like this. Really, Jeff? You choose now to be all precise? I can't even be precise. Okay. And then the cubic function, I guess how this is just a cubic function raised by 1. So I know a cubic function looks like this. And now it's just shifted up by 1, so it's going to come in like this. So if you wanted to, you could put in like negative 0.5 to really figure out exactly where that thing is. But I don't need anything too precise here. Right. These should probably be more symmetric, but oh well. So what is that all right? So I could have plugged some points in to get more precise, but that's okay. What would this represent on the graph?
The area under that line right there.
Yeah, the area between
0
the x-axis and the black line, right? And of course, this would represent the area between the x-axis and the red line, between 0 and 1. Okay. So of course, what would this represent? That little bulgy area here. Oop. I like it. So this question could have said, find the area bounded by the two functions in the first quadrant. That could be a problem that you would see in the homework. So you find out where they intersect. You only care about the first quadrant, so it would be from 0 to 1. If I would have said find it in the second quadrant, then you would have had to worry about this area down there. Okay. So what's the first thing you would do to evaluate this integral down here?
The integral first.
Well, what's the nice thing you could do? Come on. Can't you just subtract those? Don't you get this? Yes? What does this function have to do with this picture? What is this function? Isn't that a new function? That's a brand new function, x minus x cubed. What does it have to do with this picture? Is that function on this picture somewhere? No. That function is not on that picture anywhere. But we are claiming that this area is equal to this integral. Yes? So again, this is the whole idea I was talking about earlier. If I plotted that function and I got that area between the x-axis and this function is equivalent to this area. So this is neat because we're about to get into some pretty trippy stuff. We got some pretty trippy stuff coming soon. And the more you understand that an integral can represent something that the function does not immediately lead me to. Let me see if there's a better way to say that. Does that make sense? X minus x cubed. It has nothing to do with the question directly. It has nothing to do with the area directly. It is a completely different area that just happens to be the same as the one that they asked before. Maybe? So it's this whole idea I can reorganize shit. So the integral I end up working with might not be directly related to a visualization of things. And that's going to be really important when we start doing something involving volumes later. Okay. Somebody knows where I'm going with that? Okay.
Yeah.
So this one's pretty easy, yes?
Yeah.
Nice thing 0 makes it all 0, so when I plug a 1 in, 1/2 minus 1/4 is 1/4. Woo! Double check me on that. I don't know if I trust myself. So there is a level of just computational problem, right? There's a level of area between two functions, take the integral of the difference, whoop-de-doo, right? Why did I write it like this, though, specifically? Why did I put the x plus 1 here? Because it's on top. I love it, right? If I would have done this integral back here, I would have had to put the x cubed plus 1 first, yes? So that's huge. You have to know within any given little area you're looking at which function's on top, which function's on the bottom. Do they cross? Holy shit. Okay, all right. This is nice because this is all based in x like we want it to be. And of course now we have this yummy thing. So take a minute. It's always so creepy when I say it. Look at this yummy math. All right. Oh, did I end up going far enough up? Shit. All right, we'll find out. Probably not. Definitely not. Okay. All right, this shouldn't be too bad. So if you set them equal to each other, subtract, divide by 2. Jeff, don't lose your y squared. These factors, nice. Okay. So I know, now let's see if you guys can do this. Can you tell me exactly what points they intersect at?
1, 7.
1, 5.
No, 1,
There we
5.
go.
Right.
Like it. So be really careful. And be careful. What did you do to get that point? So you plugged a y in, and what'd you get for x? Negative 1 plus 6, you got 5. So x is 5, y is 1. That's just one little example of how we're not used to considering that our input is now the y, which is what we have set up as our output, which is freakadelic. I like it. And of course, when y is 5, what do I get? 5. That one you can't go wrong with. All right, let me stop for a minute. Our brains are so trained to put the number we put in first, but now that number, it represents y, it's second. What else could I find to help me graph these things? And I think I didn't give us enough room, but we'll find out. Because I changed these functions earlier, and then this is not high enough, I don't think. So I know they cross at 5, 1. So that's a common point. What kind of funky ass scale you got here, Jeff? All right. 5, 1 and 5, 5. Okay, let's do this. There we go. So notice where they cross. What kind of parabolas are these? Are they both facing the same way?
No, the first
No?
one's
This one is facing, this one opens in which direction?
right.
Yeah, so it's going to look like this, yeah? And the other one, of course, is going to look like that. So it's probably going to be like this and like this. So you're going to have this funkadelic egg-looking shape that's between the two. So couldn't I figure out, for example, couldn't I figure out the vertices? Yes? How do I figure out the vertex of this? You guys remember the shortcut? Negative something over 2 something? Negative b over 2a. So it'll be negative 6 over twice a. But what is that equal to? No, I know it's 3, but what is it equal to? What variable?
X.
No.
Y.
Y. Because now it's all about the y. So what's the x piece when y is 3? Maybe it's okay. Maybe I was thinking the wrong way. Okay. Right? 1, 3. Is that cool? When you put a 3 in for y, you get a 1 for x. Is that cool? So that's 1, 3. Let's do this in different colors. This will be in black, and this will be in red. Oh, shit. I got to leave a little early because I got a meeting. I'm sure you guys are like, oh, no. Okay. Let's see. 1, 3. Okay, so that's enough to do that, basically. I mean, that's pretty much enough to do this, right? A rough sketch, anyway. Oh, shit, where am I? There I am. Oh, this poor little thing. Somebody sat on him. All right, he's going to be okay. Leave him alone. Now, what about this guy? What's this guy's vertex? So it'll be negative 6 over twice negative 1, so it'll be 6 over, 2. So it'll be 3 again. It kind of makes sense, right? But now when y is 3, what's x? 9. So 9, 3. You can do it, Jeff. There it is. And then it shares these points here, right? So now that's enough for this guy. So the area bounded between these two functions is right there. Looks like an alien take me to your leader. Okay. So you literally can do this. Which function is on top? Yeah, the red one. Negative y squared plus 6y, right? That's on top. That's on the bottom. So now we know. And yes. Sorry? Oh. So if I have ay squared plus by plus c, y equals negative b over 2a. Yeah. And of course, with the x squared, it's x equals. All right. And earlier this semester, I showed you how you get that with calculus, which is a lot quicker than without calculus. How am I going to set up this integral then? What's going to be back here? What's going to be here? D what? dy. Kick ass. And I know the red, we're going to worry about the limits in a minute. The red one is first. So that's negative y squared plus 6y minus, and Jeff, oh my God, dude. Will you ever give yourself enough freaking room? No. So the red one on top minus the black one on the bottom. And what are the limits going to be? What do I have to look at to figure out the limits? Look at this guy. What do I care about? What are the y's doing? They're going from what to what?
Oh.
They're going from 1 to 5. Do you guys see that? And in fact, isn't that... Not always. Be careful. I got to be careful. That's not always. But in this case, because that was kind of like the limits of this, that's the limits of the integral. So now you got to think everything in terms of y. So what... And really the nice way to think of this is the integral is kind of like scanning this. It starts here and it scans up to here. And in there we would make our rectangles and shit. Okay, maybe. So I want this to be 1 to 5. And now I don't care. Now it should be easy. Right? Get your like terms together, anti-differentiate, plug the points in. Yes? Once you get the integral set up, it should be, depending on the function, it should be easy going after that. Okay, maybe. Okay. Let me think. What was the other thing I wanted to do? What time we got? We're good, Jeff. Let's see. What is this? 1 to 5, negative 2y squared, plus 12y, plus 10, minus 10, Jeff. Derp. And then, yeah, I literally don't care, to be honest, because now it's easy shit, right? Okay. Yeah, you can put these together, of course. Yeah. And again, like I said, something is really intriguing. Here you can see the concept. You can see the concept here. Top function minus bottom function is going to leave you with the area between the two. Once I combine them, this function is not here anywhere. It just is a function, the area for which is the same as the question. I really want that to make sense. Just like I took the circle and made it a frickin' rectangle. Didn't we do that earlier? We made a circle into a rectangle. And then the rectangle's easy. So effectively, I'm taking an area that I don't know, and I'm making it, into something that has an equivalent area, but is easier to directly work with. Roughly. Say again? Sure. So it'd be negative 2/3 y cubed plus 6y squared minus 10y from 1 to 5. And I'm having a lot of trouble giving a shit here. All right. I really hope you understand. Wouldn't you just plug numbers in? All right. I don't care about that. We can all plug numbers in. So you plug a 5 in, whatever the hell that is. minus, plug a 1 in, whatever the hell that is. Just a bunch of calculator work now. Okay. I really hope you forgive me for saying that. I love all of math. But this is not very interesting. You just plug stuff in. Who cares? Okay, maybe. All right. I think that's plenty. So that's section 6.1. That is section 6.1. And I don't want to make you guys worried. Well, there you go. Way to not do what you wanted to do just by saying what you didn't want to do. But the stuff we're about to get into is really, I think it's nifty as hell, which really should worry you. I have visual aids, actual physical visual aids that I will use. And as I say that, I'm like, God, I hope I can find it. Have you guys ever seen the Christmas ornaments that you, or even, we had a turkey when I was a little kid, that you would open it up, and it'd be this floofy thing. I don't know if you guys, like it's flat, and then you open it, right? Okay, somehow that is going to relate to calculus. We're going to integrate a floofy turkey.
You ruined Thanksgiving for me.
That's
We're going to floof the turkey, not the pig. All right, guys. That's enough.